Morning, everybody. So I hope everyone from the bus made it. The first talk of the morning session is Timur Oikhberg, continuation of yesterday's talk on free Banach lattices, lattice homomorphism, and nonlinear theory of Banach space.
Hi. Good morning again. So I will continue talking about free Banach lattices today. And today, as the title suggests, I will talk about lattice homomorphisms between those three lattices. And it turns out that this somehow ties into nonlinear theory of Banach spaces. And let's see. For some reason, the slides don't want to shift. Oh, so I should point at the computer.
It goes with some delay, maybe.
Oh, yeah. All right. So maybe I should stay closer to the computer so it will work better. Oops. Oh. No, it's not. it only obeys you. It doesn't obey me.
No, now it's.
Maybe I can just push buttons on the computer.
That's the other option, but yeah, maybe I'll change that. You can start on the
Okay, so anyway, so here is what I was talking about yesterday. So this is essentially the definition of a free p-convex Banach lattice. This is a Banach lattice which is p-convex with constant 1. There is a linearly isometric embedding of the space Banach space on which we are building into this Banach lattice X. And the most important property is this existence of an extension. So if Z is a Banach lattice, which is P, once again, we are working in a setting which is P of P convex with constant 1, then any operator from T from E to this Banach lattice Z extends to a lattice homomorphism T hat from the corresponding free Banach lattice back into Z without changing the norm. So this existence of the extension is described by this commutative diagram here. And as I said before, when P is equal to 1, then essentially there are no restrictions on the target Banach lattice Z. And in this situation, we will get just the free Banach lattice, which and I will omit the upper index here. So another thing that I mentioned yesterday was the functional representation of the free Banach lattice. So here I define the space of positively homogeneous functions on the unit ball of a star, which I denote by H of a star, and I impose on it this norm that once again is described here on the on the slide, and I also define an embedding of E into H of a star, which I denote by phi sub E. So I map an element X of E into the evaluation function at X. So basically, the way it works is that I just evaluate any element, if I want to evaluate this function at X star, then I just use the dual action. And I mentioned yesterday that first of all, this map phi is actually an isometry, and the Banach lattice generated by the image of phi inside of HP is the free Banach lattice, which has this nice extension property from the previous slide. And here I should mention once again that all the elements of the free Banach lattice, they are not just functions on the unit ball of a star, they are weak star continuous functions on this unit ball. And very often it's convenient to extend the functions from the unit ball of a star to the whole of a star by positive homogeneity. Well, and in this case, they will be big star continuous on bounded subsets of a star. Now, it turns out that the case p equal to infinity is special because in this situation, the infinity free Banach lattice will coincide with the space of all positively homogeneous big star continuous functions on the unit ball of a star, and the norm there.
It's not working,
Oh, okay.
but you can use the pointer if you
Oh,
want.
the pointer will be helpful, and the norm coincides with the infinity norm. So this is essentially a brief review of what I talked about yesterday. So let's see any questions so far about this. Well, so let's move on to the new material. So we first try to determine, well, let's say we have a Banach space C, so under which conditions the P-free Banach lattice is the same as the Q-free Banach lattice. So essentially we want to determine in what conditions can we vary this exponent P versus Q. To answer this, it turns out that we have the following theory. So for a Banach lattice, so let's say we have a Banach space E, and let's say P and we have P and Q, so that P is greater than Q, and well, as usual, Q is greater or equal than 1. Then the following statements are equivalent. The first one is that the Q convex free Banach lattice is P convex. So let me remind you maybe the definition of convexity. Yeah? So in general, we say that the Banach lattice Z is, say, R convex with constant C. If for any n tuple of elements of this Banach lattice capital Z, we have that the norm of the sum of Zi to the power R, then we take the R's root, we take the norm. This is less than or equal than C times the R's root of the sum of the norms of those Zi's. So in general, if you have two numbers, say U and V, and if U is less than V, then V convexity will imply U convexity. So as far as convexity is concerned, the smaller the exponent of convexity, the easier for us to verify this condition. In this situation, this Q-free Banach lattice, of course, is Q convex by definition. So here we are imposing a stronger condition of it being P convex. So this is equivalent to the P convex free Banach lattice B on E being lattice isomorphic or canonically lattice isomorphic to the Q convex Banach lattice. So what does canonically mean? Well, there is a copy of E sitting inside of each of those three Banach lattices. So canonical lattice isomorphism is the one which gives you the identity on E. And the last equivalent condition is a factorization condition. So if you have a map, if you have a linear operator from E into an LQ space, then it will factor through an LP space. So here, of course, the map from E into LP is a bounded operator, and the map from LP into LQ is an operator of multiplication. And of course, G has to be such that this multiplication operator is bounded. And this kind of factorizations have been studied from the early 1970s, from the work of Murray and Nikishin. So we have several examples where such a factorization exists, and consequently, we have this identification between the P3 and the Q3 Banach lattice. So one case I should mention is that P and Q, well, we have this kind of inequality between P and Q and S, and let's say the space E has type S, then we have this canonical lattice isomorphism, or equivalently, we have the P convexity of the Q3 Banach lattice. And another situation is we are building a free Banach lattice on R, and P is less than 2, then the P free Banach lattice is the same as 2 free Banach lattices. So in other words, we have that this P free Banach lattice is 2 convex. And in all those examples in the corollary, you see that the P and the Q I'm dealing with are sitting between 1 and 2, and this is not by accident. So it turns out that if we have an infinite dimensional space and the P3 Banach lattice is Q convex, then Q cannot be more than the maximum of 2 and P. So if P is less than 2, then in theory we can have that this free Banach lattice is Q convex. But well, let me maybe explain this in a little bit. But first let me mention that of course the infinite dimensionality condition is essential, because if we start with an n-dimensional space E, then we know that the corresponding free Banach lattice is lattice isomorphic to a space of continuous functions on the sphere. And of course, here you have convexity for any Q. But now going back to the case when P is greater or equal to infinity, then well, from the definition, this P free Banach lattice is P convex, and this theorem states that this cannot be improved. So this P free Banach lattice cannot be Q convex for Q greater than P, and this means that if a Banach lattice is infinite, if a Banach space E is infinite dimensional, and well, the P3 and the Q3 Banach lattices are lattice isomorphic, then well, either P is equal to Q, or P and both P and Q are both in the interval from 1 to 2. So these are the only situations when we can have a this P and Q being between 1 and 2 is the only situation when we can have a non-trivial lattice isomorphism between those two free Banach lattices. So this is what happens if we try to change the quote-unquote freeness exponent here. What about changing? The underlying Banach space? So under what conditions, in other words, can we have a lattice isomorphism between the P3 Banach lattices of E and F? Well, it turns out that here we have this remarkable result, and I hope I'm not mistaken in the attribution. I think it's due to Niels Laus and Pedro Tredasete. So I hope I'm not omitting anyone, or I'm not making any mistake here. So let's suppose that we have a lattice homomorphism between those two free Banach lattices here. Then, well, essentially you can represent this lattice homomorphism as a composition operator. More specifically, there is a positively homogeneous mapping now from F star to E star, which is weak star to weak star continuous and bounded sets, so that for any Y star in F star, well, and F in the free Banach lattice, well, we have this kind of identification. And we also have this easy estimate that the norm of phi t applied to Y star is no more then the norm of T applied to this Y star. And actually there is a moreover part to it. So first of all, if P is equal to infinity, then the converse is also true in the sense that if you have a weak star continuous to map on bounded sets, say phi, then it will determine a lattice homomorphism. So there will be a lattice homomorphism T, so that phi T is phi. So the composition with phi gives you a lattice homomorphism. And as we shall see, this is not going to be the case in the case of finite P, but in the case of finite P, we can also have we know something else. So if Q is greater or equal than P, then we have this inequality for the weak star norm, for the Q weak Razi norms of n tuples in F star. And well, let me briefly remind you what these weak star norms are. So if you have what these cubic norms are. So let's say you have an n tuple of yi star, then its cubic norm is you can think of it. Well, there are many ways to think of it, but one is to take the supremum. Well, maybe I should write here the supremum of all the norms of the sums like lambda I times yi star, and the supremum is taken over all the sequences of lambda, so that the sum of lambda to the power q prime is no more than 1. Q prime is the conjugate exponent of q. And now, since we are interested in this, specifically in the case of T being a lattice isomorphism, then, well, for lattice isomorphisms, we have, of course, T inverse. So the corresponding maps phi, they are inverses of each other. So I know that this is quite a long theorem, quite a long statement. So I will remind you, I will put it back on the slide several times as needed. So here is, by the way, a different formula for the cubic norms that I put on the slide. So here is once again the same theorem. And well, let me at least give you an idea of how this is proven. So first of all, how is the map? Where does the map phi sub t? Where does it come from? Well, you look at the operator T star, which now the operator T star, which will go from the dual of one free Banach lattice to the dual of the other, and T itself is a lattice homomorphism. Therefore, its dual is adjoint T star will be interval preserving, and in particular, it will map atoms to atoms. So if you look at the atoms of of the dual of this free Banach lattice, well, we know that those atoms come from evaluation maps, and well, as I said, T maps from atom to atom. So if for any y star in F star, the image of it will be some x star, and then this is what defines your phi sub t. And then you have to show that it has the desired properties, such as positive homogeneity and weak star continuity. But this is fairly straightforward. Now next, what happens to the cubic norms? Well, this here I also want to recall something that I said yesterday. So let's say you have an n tuple, then the n tuple in F star, then the cubic norm of this n tuple is the same as the cubic norm of the corresponding evaluation functions. And these evaluation functions here, they are, well, now they're in the dual not of F star, but they're in the dual of the three Banach lattices built on F. And then, well, of course, the map of T star is the same as the norm of T star is the same as the norm of T, and therefore this will hold. And well, this is essentially the end of the proof, or the end of the brief sketch of the proof. Here, let me maybe say a few words. So the first one is that, well, it's if you just look at the n-tuples for n equal to 1, if you just look at singletons, then for singletons you get this estimate of the norm that the norm of phi t of y star is no more than the norm of y star times the norm of t. And if t is a lattice quotient, then this phi sub t will also be bounded below. So there will be an opposite inequality as well, but of course with a different constant. This theorem shows that to study lattice homomorphisms between three Banach lattices, it is let's just say advisable to study nonlinear maps between Banach spaces. And here I want to take a little detour to say maybe a few words about what is known about such nonlinear maps. And it's not really part of the proofs or anything. It's just so that we will have an analogy and maybe understand some of the motivation. So of course we know that the nonlinear theory of maps between Banach spaces once again has its roots, I think it's in 70s and at least, well, actually earlier in the 60s. First, people were looking just at continuous maps between Banach spaces, and continuous maps turned out to be not very useful. And there is this theorem which was first established by Kazets in, I think, the 1960s, and then a little bit later. So Kazets established it in the separable case, Karunchik later in general. So if we have two Banach spaces E and F which have the same density character, then they are topologically homomorphic. So there is a linear there is a continuous linear map with a continuous inverse. Not linear. Sorry, non-linear, continuous non-linear map. Thank you for correcting me. Continuous non-linear map. And therefore, to be able to build meaningful theory, people needed more restrictive classes such as Lipschitz, uniformly continuous, coarse, whatever. I just want to mention a few things about the Lipschitz maps, just so that we will get a flavor and maybe figure out what to expect. So first of all, in certain situations, being Lipschitz isomorphic implies being linearly isomorphic. So let's say we have two Banach spaces E. One of them, E, is separable and reflexive, and let's say it's Lipschitz isomorphic to some F. So if F has the RNP, and I'm not going to tell you what it is, if F has the RNP, then E has to be linearly isomorphic, not necessarily to F itself, but to a complemented subspace of it. And well, under some technical extra conditions, actually, E will be linearly isomorphic to F itself. So under certain conditions, being Lipschitz isomorphic implies being linearly isomorphic. So so in particular, this happens when F is either capital LP or little LP. So if E is Lipschitz isomorphic to either one of those two spaces, then actually, sorry, if E is Lipschitz isomorphic to either little or capital LP, then the two spaces will be linearly isomorphic as well. However, in general, well, here is also another result that if E is Lipschitz isomorphic to a subset, and here, it doesn't have to be a linear subset of F, then E actually embeds linearly into F double duo. So you may ask, well, does Lipschitz isomorphism actually imply linear isomorphism? And the answer is not. Oops. The answer is not. There are examples of this. So there is it may so there exists an uncountable set gamma, so that there is a pair of spaces E and C0 gamma, which are Lipschitz isomorphic but not linearly isomorphic. So even with Lipschitz, weird things can happen. And all this has to do with Lipschitz isomorphism. Well, it turns out that if instead of isomorphisms, you look at isometries, then well, isometries are more restricted. Isometries are more rigid. And let me start here by mentioning this theorem of Mazur and Ulam that any surjective isometry between Banach spaces is affine, and therefore, if two Banach spaces are metrically isometric, they are also linearly isometric. Non-surjective isometries, of course, needn't be affine, but for non-surjective isometries, we still have a theorem of Figel. So if we have two separable Banach spaces, and if we have an isometry one into the other, so let's say the image of the isometry spans the spans the space, the target space Y, and just by translation, we can always assume that the isometry is zero preserved. Then in this situation, you can lift. Well, you can go from Y back into X. So you almost have a linear inverse, and consequently, if we have a separable Banach spaces and we have an isometry, then the target space Y will contain a linearly isometric. Well, here I wrote isometric. Here I meant linearly isometric copy of X. So this kind of leads you to expect that the isomorphic case will be different from the isometric case, and from what I know now, it looks feasible, but also there will be a difference between the case of P being equal to infinity and P finite. So let me just say a few words about what when can we have a lattice isomorphism between those two free Banach lattices built on the end of that. So this is the diagram. Once again, I'm plagiarizing from myself. You must have seen it on my slides yesterday. So let's say we have a map T from F to E. Then you can extend it to a map T bar between the corresponding free Banach lattices. And of course, if T is an isomorphism, then T bar is an isomorphism. If T is an isometry, then T bar is also an isometry. And here I should say that when I'm talking. Should I maybe hold the mic?
No, there's no mic.
Oh, but what is making? Oh, okay. Well, no noise. Okay, so by objective isometries here. Oops. Oh. On the telephone, hopefully it's not.
Sorry.
No problem. So let's move on. So if A and F are the same essentially, then the corresponding Fibonacci lattices will be the same. And kind of the interesting question, can it happen that A and F are different, but the Fibonacci lattices are the same? And as I said, the case of P being equal to infinity will be different from the finite case. The isometric and isomorphic case are treated differently. And here is once again, I'm putting back this theorem of Nielsen and Niels Lauston and Pedro Tredeseta, which characterizes lattice homomorphisms between three Banach lattices. And let me handle the case P equal to infinity first. And in this situation, well, once again, we know that these three Banach lattices on A coincides with the space of weak star continuous, positively homogeneous functions on the unit ball of a star equipped with the subnorm. And if we specialize this characterization of lattice homomorphism between three lattices into the case of P being equal to infinity, then actually we have an if and only if characterization. So first of all, any positively so on the previous slide, here we had that any lattice homomorphism is a composition map, and in the case of P being equal to infinity, we have the converse. So any weighted composition, provided of course we are composing with a positively homogeneous function weak star continuous on bounded sets, any composition like this gives rise to a lattice homomorphism on three Banach lattices. And if phi is surjective and we have this kind of inequality, then the corresponding map will be actually a lattice isomorphism, and we will have bounds on the norms of T and its inverse. Under what conditions will the infinity three Banach lattices be the same? Well, here I need to introduce this definition of a finite dimensional decomposition, or FDD. So this is in a sense a generalization of a basis. So what it tells us is that, well, in a Banach space E, we have an increasing sequence of projections Pn, so that, well, they are commute in this way that if we multiply two projections, then we get the projection with a smaller index. And also we need to require that for any x in the Banach space, it's the limit of the images of those projections gives us x itself. And by closed graph theorem, then you can conclude that the norms of those projections are uniformly bounded. And yes, the projections are finite ranks. That's why we call this finite dimensional decomposition. And this, you can think of this notion as a generalization of a Schauder basis. So if in a Schauder basis you get the canonical projection onto the first, say, I elements of the basis, then this Schauder basis projections will behave precisely in this manner. we specifically are interested, or I will want to work rather maybe with monotone FDDs. So monotone means that all those, well, here I wrote the soup, but I could have avoided the soup. Well, in FDD is monotone if for every index n, the norm of this projection is equal to n. Of course, it cannot be less than, sorry, it is equal to 1. Of course, it cannot be less than 1, but so this is in a sense the best or almost the best possible FDD. And of course, bases in classical symmetric spaces such as LP spaces will give us an example of such an FDD. And in a result which I think it's pretty surprising is the following: that let's say we have a Banach space with a monotone FDD. By the way, having a monotone FDD, having an FDD will force it to be separable. Well, so if we have a monotone FDD, then the free Banach lattice, the infinity free Banach lattice on E will be lattice isometric to the free Banach lattice on C0. So let me maybe see why this is true, or try to explain why this is true, and but kind of in a PG-13 version. So I'll instead of an FDD, I want to consider a Schauder basis, and I want to strengthen the condition of monotonicity. I want to make this basis strictly monotone. So strictly monotone is the following: that if you add, so monotonicity gives you that for any collection of for any if alpha is a collection of real numbers, then we always have this inequality here, that if we add a different coordinate, the norm will not decrease. But strict monotonicity tells you that the norm will actually increase unless this extra coordinate that you are adding is 0. And the goal, I call a construction, is that if E has this strictly monotone basis, then I want to construct a positively homogeneous surjection which preserves norms. So it doesn't mean that it is an isometry. It just means that it preserves the norm of any given vector. It does not. It's not an isometry because it does not preserve distances. So you want to go from a star into L1, and you want to make sure that the map phi and its inverse are weak star continuous on bounded sets. And so notation-wise, we already had the vectors EI in E, and EI star will be the bi-orthogonal functionals, and let's denote Fi star by Fi star the canonical basis of L1. And let Pn be the end basis projection, in this situation, Pn star takes E star to this span of EI stars as I runs from 1 to n, and we denote this span by Xn. And we will construct a sequence of maps phi n from Xn to Yn. And I cannot explain what Yn is, but for Yn, Yn is a similar span, as Xn is the span of AI stars, then Yn will be the span of Fi stars. So Yn will be the corresponding, let me maybe write this, so that it will not be lost. Okay. It reminds me of the good old time back behind the Iron Curtain when you want to listen to some Western radio stations, and there is some noise generator on the background trying to prevent you from listening. So I hope you can still hear what I'm saying. So in any event, so we define as a map phi the sequence of maps phi n from xn to yn, and we define them recursively. So when n is equal to 1, then we just take the alpha 1 E1 star, we take it to the corresponding multiple of F1 star. So this, and if we go beyond this, let's say phi n minus 1 has already been defined on xn minus 1. So then if we have a vector, this should be E star, there should be no index n here. So if we have a vector E star in xn, so this E star can be written as x star comes from xn minus 1 and then plus some multiple of En star. So then we define the image of this E star as the image of x star plus a corresponding an appropriate multiple of Fn star. And what is it appropriate? Well, so first of all, we have to take care of the sign of this alpha, and then we have to multiply this by E star by the difference of the norms. And the reason we take this difference of the norms is that we want this phi n to be isometric. And this difference of the norms, this will be non-zero unless, of course, alpha is 0. But if alpha is non-zero, then this difference will be positive. So the map is well defined. The map phi n will then be bijective, and then we have to kind of glue them together. And we just compose them with corresponding projections P and star, and then we take the weak star limit, and then now the hand waving part, I say that this map phi will have the desired properties, namely the weak star continuity on bounded sets for the map and its inverse. So here we use strict monotonicity. Now, if you don't have monotonicity, if you have just monotonicity, then you have to jump through some technical hoops. If you have an FDD, then you have to somehow make certain changes here. But the big question from my standpoint is that whether we can get rid of the FDD assumption, because now it seems that we are using the FDD assumption almost like a crutch, and maybe we can work without it, but maybe not. So in any event, so going back, let me restate this theorem from 2 slides back. So I have this. Whenever we have a monotone FDD, then we have the infinity free Banach lattice is lattice isometric to this particular one, which I will denote by U by this fractal U for universe. And the question is, so as I mentioned before, what can we do without the FDD assumption or without the monotone FDD assumption? Well, first of all, if we relax monotone FDD to just FDD, then we just get a lattice isomorphism to this universal object. If so in general, if we have a separable Banach space, then the identity on this free Banach lattice of infinity free Banach lattice of A, it factors through this object U. So in this factorization, J is just a linear isometry, and then we have a contractive lattice homomorphism from U back into FBL infinity of E. So this is not a lattice factorization because J, we don't know what the lattice property of it are. Or well, sometimes we actually do, because if well, this is F, this should be E. If E has a bounded approximation property, then J can be made to be a lattice isomorphism, to be a lattice isomorphism. So if in the BAP case, we actually do have a lattice factorization. Well, I should say that if I remember correctly, in the BAP case, to make J lattice isomorphism, we may need to sacrifice the isometry part. So let's see. Let me skip the proof because we are now kind of short of time. So the question that I would like to advertise is, what can we say about this universal object? What are its properties? And one thing that I can say is that I cannot answer the question what it is. I can at least partially answer the question what it is not. It is not a Gurari, or it is not a homogeneous lattice. So homogeneous roughly means that if you have a finitely generated sublattice in one position and the the identical finitely generated sublattice in the other position, then you can move one to the other. Well, here we don't even have this property in the for one-dimensional sublattices. But this is a general fact about the free Banach lattices, because if we have for any E and any P, we can always find two positive norm one elements in this free Banach lattice, so that for any lattice isometry or T lattice isometry on this free Banach lattice, the image of one will be far from the image of the other. So you cannot move. There are always there are always two vectors which cannot be moved one into the other. So this is one thing, and another is a Banach space characterization. So on the Banach space level, this universal object is isomorphic to C01, but this is just an isomorphism, and I cannot really control the isomorphism. So in the separable case, actually we don't know of any example of a free Banach lattice, so that we don't know any examples of a separable Banach space E, so that the corresponding infinity free Banach lattice is not that same universal object. And it may well be true, and there is a kind of, it's not the reason, but maybe part of the, maybe by analogy, I should mention that in a sense, topologically, duals to separable Banach spaces are the same. This is the famous theorem of Keller, that if we have two separable Banach spaces, then the dual walls equipped with the big star topology are all equivalent, they are all homomorphic to each other, and actually they are homomorphic to the Hilbert cube. So at least from the topological standpoint, the unit walls of duals are the same. And this is not the case in the non-separable case, in the non-separable setting. There are many, of course, in the non-separable settings, there are many different topological peculiarities, let's just say. So one is the following. So let's say gamma is a certain set with a cardinality more than continuum. P is in the reflexive range. And let's consider two spaces, L1 of gamma and LP of gamma. So they have the same density character, but the dual balls are not topologically homeomorphic to each other. And you can also show that the corresponding free Banach lattices are not lattice isomorphic. So in the non-separable setting, things will be much more difficult. And we don't know much about that. And so instead of talking about the non-separable setting, let's talk about the situation when P is finite. So here is again the same remarkable theorem of Lausten and Redesset, is the same description of lattice homomorphisms. And here in the case of finite P, there arises an additional difficulty. So there are compositions, namely as this theorem tells you, that any lattice homomorphism is a composition operator, but there are composition operators which are not lattice homomorphisms. More specifically, you can find a positively homogeneous function from L infinity to L infinity, or the way I wrote it, from the dual of L1 from the dual of L1 to the dual of L1, so that the cubic norms are preserved. It's weak star continuous and bounded sets, but it does not. But the corresponding composition operator does not define a lattice homomorphism on the free Banach lattice. So it may happen that if you start with some function f in the free Banach lattice, but if you compose, you get out of this free Banach lattice. So this is related to this example of Aviles, Rodriguez, and Redesset, which tells you that that if you look at the free Banach lattice inside of the HP, then it's not going to be a lattice ideal. So this tells you how bad things can be. So it's here I want. So here my question is, under what conditions the P free Banach lattices on E and on F are different. And to tell the truth, I don't know of any examples when those free Banach lattices are the same, unless E and F themselves are the same. But at least in certain situations, we can prove that those Banach lattices are different. And instead of lattice isomorphisms between those, I will talk about a more general setting of lattice quotients. So here is the theorem. So let's say we have two numbers, u and v, between 2 and infinity. The index p and b is between 1 and infinity. So, and then let's say we have this kind of conditions on u, v, and p prime. And let's suppose that E star has cotype U, and F star doesn't have cotype less than V. So in this situation, the P free Banach lattice on F is not going to be a lattice quotient for the free Banach lattice on E. And so first of all, let me remind you what it means, for instance, to have cotype U. So it means that for any n tuple of elements of a star, the expected value of their sums with plus minus signs is greater or equal than this quantity on the right. Well, on the left, instead of the expected values of their sum, you could have taken the expected values of the piece power and then the piece rule. This will all be equivalent by Keynesian-Kagan theorem. Another thing is that, of course, if you this inequality here, this condition gets less and less restrictive as u increases. And if u is infinity, then this will be true by the triangle inequality. So every Banach space has cotype infinity. The tricky part is, which is called also the trivial cotype, and the tricky part is about finite cotypes, so non-trivial cotypes. well, that's probably all I wanted to say as an introduction. The canonical examples here are LR spaces. So we know that LR has cotype which is the largest of R and 2. Oh yeah, that's what I wanted to say. So this cotype constant, this cotype exponent U cannot be less than 2. And this can be verified just by looking at the one-dimensional situation. And if you have a one-dimensional space, then you can clearly see that you cannot have less than 2. LR has cotype that will be equal to the maximum of R and 2. Here, as a corollary of this theorem, we can say that, well, let's say we have alpha and beta. So beta is between 1 and 2, alpha is between beta and infinity. Then the free Banach lattice of L beta is not a lattice quotient of the free Banach lattice of L alpha. And it's kind of a classical fact that in this situation, L beta is not going to be a quotient of L alpha in the usual sense. So this result about the quotients of free Banach lattices is a generalization of this well-known fact. And the proof is a fairly straightforward application of this theorem here. So you take E to be L alpha, you take F to be L beta, you take P to be 1. By the way, I formulated this corollary for P equal to 1 just for the sake of simplicity. When P is equal to 1, then of course P prime is equal to infinity. So our U, our E has a cotype which is the maximum of 2 and alpha prime. This will be our U, and beta prime will be our V. And this V is greater than U, so just an application of the theorem will get you the corollary. So what else do I want to say? So here I prepared the proof of this theorem, but once again, let me skip it for the sake of not keeping you too long in this lecture. There is also a somewhat similar result. So once again, we want to show that one free Banach lattice cannot be a lattice quotient of the other. So now let's say once again we have U and V which are now satisfying this inequality. Let's say our space E is a direct sum of finite dimensional spaces in terms of U. And let's say further that F star contains a copy of LV prime. So in particular, where of course V prime is the conjugate exponent, then the P free Banach lattice of F is not a lattice quotient of a free of the P free lattice on U. So there are so in particular this condition will be satisfied with when F is equal to LV. So LV is not going to be a lattice quotient of anything of this type. So there are many results on this of this type, but these are somehow technical and involve a certain type of vector versus subspace game in Banach spaces, and these are somewhat related to the notion of asymptotical p-ness. And here, let me ask a few questions which are somehow related to all this. So one of them is something that I mentioned before. Does there exist Banach spaces E and F which are themselves not isomorphic, but the corresponding P convex Banach lattices are isomorphic? This is once again something that I don't know. And another question, well, let's suppose that we got lucky, we discover E and F, which are Banach spaces E and F, which are not themselves isomorphic, but the corresponding free Banach lattices are isomorphic. So nevertheless, if in this situation, which properties will E and F share? So you may also ask whether somehow how do properties or maybe to say it another way, well, if let's say E and F share a certain property, is there a corresponding property to be shared by the free Banach lattices? So we kind of have a partial answer to this question. So let's suppose that, and this has to do with something that I mentioned in the previous lecture. So let's say E, the space E contains capital L1 as a complemented subspace. Then we know that the free Banach lattice, when P is equal to 1, the free Banach lattice on E or contains L1 as a complemented sublattice. Now, if the free Banach lattices of A and F will be isomorphic, then the free Banach lattice of F will contain L1 as a complemented sublattice. And then F will have to contain L1 as a complemented subspace. And we have the same result where we can reach the same conclusion if E contains L1n's uniformly complementably, then the same will be true for F. And now I want to move on from lattice isomorphisms to lattice isometries. So when it comes to lattice isometries, then we can come up with more proper, or at least we can discover some properties that do pass between E and F if E and F are if the corresponding free Banach lattices are a lattice isometric. And one of those properties is so-called strict convexity. So I put the definition here, but maybe it's better to illustrate it with a picture. So this is maybe do it differently, maybe smaller. So let's say this is a unit ball of Z. So what does it mean that Z is strictly convex? Well, let's say we take Z1 and Z2 on the unit sphere on the surface of the unit ball. So this is the origin. You link Z1 and Z2 by a line segment. You take the midpoint of this line segment. The midpoint will be the interior in the interior of the unit ball, or equivalently, this whole line segment will be in the interior except for the endpoints. And so this is strictly convex, and the lack of strict convexity would mean that the unit ball would have to look like this. There will be a line segment on the surface of this unit ball. So this is the definition, and as a warm-up, let me try to show this proposition that, well, or at least state this proposition. Let's suppose that we are in the P convex, the P is in the finite range. The P free Banach lattices for E and F are lattice isometric. And then, well, the duals of E and F are either both strictly convex or both fail to be strictly convex. So here I should note that strict convexity of the dual implies smoothness of the space itself, but the converse is not necessarily true. So let me try to give you a proof what happens when P is equal to 1. So let's suppose that F star is not strictly convex. And let's say we have a lattice isometry between those three Banach lattices, except that this P should be 1. And well, actually, I did take this into account. I was talking about the 1 week norms here. So so here I'm just making an observation that if we have two elements, X star and Y star, in say F stars, then what can we say about the 1 weak norm of this pair? So this 1 weak norm is just the maximum of the norm of X star plus Y star, X star minus Y star. And thank you. Thank you very much. The 1 weak norms are preserved, and therefore we have the maximum of X star plus minus Y star will be the same as the maximum of the same thing with phi t. And now I want to work with special X star and Y star. So I'm assuming that F star is not strictly convex. So I want to pick Z1 and Z2 in F star on the unit sphere of F star, so that the sum has norm 2. And now I define X star to be the average of Z1 and Z2, and Y star to be their difference. So here I should say that X star and Y star are different. Y star is different from 0, and the 1 weak norm here is equal to 1. Now I now take a map under phi t, and I denote by omega 1 to be the sum phi t of X star plus phi t of Y star. And if phi t were a linear map, this would be the image of X star plus Y star, but of course phi t is non-linear. And omega 2, W2 is defined in the same manner. So now these are elements of a star. And now what can we say about omega 1 plus omega 2? Well, if you add them, then we get twice the image of X star. So we get twice the norm of X star. So this one, this is not 1. This should be 2. And omega 2, this is a non-zero vector. But on the other hand, well, omega 1 and omega 2, neither of them, in the norms of them do not exceed the 1 weak norm of this pair. And the 1 weak norm of this pair is 1. So so maybe once again, it may be convenient to draw a picture. So what is the geometric idea of our proof? Well, we have those 2 points, Z1 and Z2, on the unit sphere of F star. So then our vector X star is here, and our vector Y star is here. And then we have this image of X star under phi t. We have the image of Y star under phi t. The length of this vector is 1. But then neither of those sums, this sum and this sum, or maybe neither of those 2 orange vectors, have norm can have norm greater than 1. So, but of course, the average of these 2 orange vectors has norm equal to 1. So what does this mean? It means that those 2 endpoints of these 2 orange vectors sit on the unit sphere of a star, and therefore this line segment belongs to, it also sits entirely on the unit sphere of a star. So here we conclude that, here I'm saying something, I'm sorry, I put something wrong on the slide. I'm not contradicting the strict convexity of the star. So here what I should have said is that this witnesses the lack of the strict convexity of a star. So I started with assuming that F star is not strictly convex, and here I end up with establishing that E star is not strictly convex. So there is this notion of strict convexity. There is also the notion of the dual notion of smoothness. So this means that a Banach space Z is called smooth if for any element, for any non-zero element, the Norman functional is unique. And geometrically, this means roughly that the unit sphere of Z has no corners. And for smooth spaces, we actually can say a few things. Let's suppose that is one of the two calls. So either both E star and F star are smooth, or they are both reflexive, and one of them is smooth. So if the three Banach lattices on E and F are lattice isometric, then E and F themselves must be lattice isometric. So in this situation, if the three Banach lattices are the same, then the spaces themselves are the same. And I'm not going to give the whole proof, or maybe I'll sketch part of it. But here maybe it's a good spot to mention the kind of the idea of what we have. So really all the proofs use this map phi sub T. And to analyze this, we know essentially two things. We know that it's weak star to weak star continuous and bounded sets, and we have access to the p-weak norms of n tuples. So for instance, when I was talking about convexity, I had to somehow reformulate convexity in terms of the one-summing norms of pairs. And this I think it may speak to the fact that our tools are not yet sufficiently well developed, or maybe we cannot develop it further. So when I'm working on this, I feel almost like a doctor before the invention of imaging techniques such as X-rays or CAT scans or whatever. So you basically just have the patients, you don't know what's inside of the patient. So you just have what you see. So what do we see here? We see that we can think of we can in general, if we have a vector X in the Banach space, we can we denote the set of supporting functions of it by f of x, and it turns out that we can describe the asymptotic behavior of the p-weak norm of the pair x comma ty, whereas t approaches 0. So x and y here are elements of the unit sphere of z. So it turns out that we have this kind of asymptotic behavior where kappa is the supremum of what you get when you test on y the supporting functionals for x. And well, here this is the I still have time to, well, at least try to sketch the proof. So this is what I want to show. So let's say E star and F star are both smooth. Then any lattice isometry between the three Banach lattices gives rise, actually, I want to show that any lattice isometry between three Banach lattices arises from a linear isometry between the underlying Banach spaces. And because of the smoothness, we know that that for any element there is exactly one supporting function. And this allows us to define on Z the so-called semi-inner product. So what is a semi-inner product for a pair of Yx? We are acting on Y by the supporting function on X. And this semi-inner product, well, it's similar to the inner product, except that we don't have symmetry, we don't have additivity in the second variable. But why am I doing this? If we have a lattice, so let's say we are in this situation, we can define the semi-inner product of E on E star and F star respectively. And I claim that our map phi sub T arising from this T preserves the semi-inner product. So if you look at the p-weak norm of this pair X T by star, if you look at the asymptotic behavior as T goes to 0, then we have this, and the same will be true for this is what happens in F star. The same will be true in E star. So this means that the map phi T preserves a semi-inner product. And there has been a quite ingenious work of Ilisevich and Turcek, which characterized maps which preserve the semi-inner product as compositions of a linear map and multiplication. I should say that not the semi-inner product is preserved, but rather the absolute value is preserved. So the synthesis A and F, they should be inside of the absolute value. The absolute value of the semi-inner product is preserved. And the semi-inner product, and therefore the map is a composition of multiplication by positive -1 and the linear map. And then you have to show that this map sigma multiplication by positive or -1 is actually constant, either it's always +1 or -1, and the linear map is big star to big star continuous, and therefore it comes actually from an isometry between the underlying Banach spaces. So there are more things that I want to mention. So maybe, but I want to, but for lack of time, I will go quickly through this. So let me mention one more result, that let's say you have now two AM spaces. If you look at the p-convex free Banach lattices built on them, then the free convex Banach lattices are lattice isometric if and only if the underlying AM spaces are themselves isometric or equivalently lattice isometric. And so let me skip the idea. And the last topic I wanted to mention is the topic of big compact generation. So this is I think historically what sparked the interest in free Banach lattices. I'll tell you more in a moment. So first of all, a Banach space E is called weakly compactly generated, or WCG, if, as the name suggests, there is this E contains a weakly compact set K whose linear span is dense in E. And the theory of weakly compactly generated Banach spaces, it's quite involved. Such spaces have certain nice properties, which I'm not going to recount now. And likewise, you can talk about a Banach lattice X being LWCG, weakly compactly generated as a lattice, if there exists a weakly, it contains a weakly compact set, so that weakly compact set K, so that X is spanned by K. Once again, will not spanned by rather X is generated by K as a lattice. So the vector lattice generated by K is dense in X. And the question asked by Joe Distal was, well, clearly Banach lattice, which is WCG, must also be LWCG. So his question was whether the converse is true, that if X is weakly compactly generated as a lattice, whether it's going to be weakly compactly generated as a Banach space. And well, spoiler, the answer is negative, but we'll get to it maybe in a minute. So here I should mention, as a way of getting to this, let me mention this proposition that, let's say, E is either an AM space or an order continuous P-convex Banach space. Then for the free Banach lattice, LWCG is equivalent to WCG. And well, now this results that I kind of just announcement. This is by Aviles, Rodriguez, and Rodeseta, that for P strictly greater than 1 but not exceeding 2, the free Banach lattice on LP of gamma is LWCG but not WCG. Here gamma has to be an uncountable set. And the idea of the proof is that, well, look at this LP of gamma. This LP of gamma is order continuous, and of course P convex, and LP, and of course since LP of gamma is reflexive, it's weakly compactly generated, and therefore the corresponding free Banach lattice will also be well. Well. So here I'm using P equal to 1, so certainly it's convex. So the free Banach lattice will be LWCG. But on the other hand, it's possible to show that if the free Banach lattice built on LP gamma contains a complemented copy of L1 of gamma, and this prevents this space being WCG. So this is the kind of sketch the proof of this remarkable theorem of Aviles, Rodriguez, and Rodeseta. And I will stop here.